Hey, Dave, do you want to stop stealing my thunder? We're going to give an introduction here. So it's my pleasure to introduce Ronald Driggers, our new faculty member here at the College of Optical Sciences, who arrived last year. Before coming to the College of Optical Sciences, Ron spent 3 years at Creole, and before that he has a long history in government and military and private research sector. Previously in 2008 he was appointed as Superintendent of the Optical Sciences Division at the Naval Research Lab. For 2008 he was the Director of the Modeling and Simulation Division at the U.S. Army's Night Vision and Electronic Sensors Directorate. He also spent a brief period as the Chief of the Electro-Optics and Photonics Division at the Army Research Lab. So Ron received his doctorate in electrical engineering from the University of Memphis in 1990. He's the author of 5 books on Infrared and Electro-Optics Systems. He's published over 160 research papers. He was the Editor-in-Chief of the Encyclopedia of Optical Engineering. He was selected as the 2002 Army Materiel Command's Engineer of the Year, the 2001 CERDEC Technical Employee of the Year, 2001 NVESD Technical Employee of the Year. He's a U.S. Army Reserve Officer and was selected as the 2001 Navy Engineering Duty Officer of the Year. He's also a Fellow of the International Society for Optical Engineering, the Optical Sciences Society of America, and the Military Sensing Symposium. He was Editor-in-Chief of SPIE's flagship journal, Optical Engineering, from 2010 to 2015, and more recently was the Editor-in-Chief of the Optical Society of America's journal, Applied Optics, from 2015 to 2021. He has triplets. He rides his motorcycle cross-country, and he plays the guitar roughly 3 times a week. So,
thank you, Dale. I appreciate it.
And today he's going to talk about advanced infrared systems.
Thank you so much. And thank you for lunch. It was great. Hey, the one thing I do want to say before I get started here is that I was really honored to come here to the University of Arizona. There's a long history of infrared here at University of Arizona. There's Bill Wolf, Dave Sterniak, and on and on. I mean, it is just fantastic. So when Tom Koch, when we talked and he said, yeah, we'd love to have you out here, I'm still on cloud 9 about it, and I really enjoy being here. This feels like home. I'm an applied researcher. You will never find me apologizing for being an applied researcher. I'm not a basic photonic light matter interaction guy. I really enjoy what I do, and it's appreciated here at this, at the college here. So.
Did you take off the mask on so we can understand what the hell you're saying?
I don't know.
You have my permission.
I got your permission. Is Tom Koch here? Cindy, can I take this mask off?
Your choice. If you'll take yours off, I'll put mine on.
All right. Does anyone in here have a problem with me taking my mask off? Dave, I think you gave your lecture last week with your mask on, right?
Yeah, but I talk loud.
Okay. All right. Is that better?
Yes.
That's much better for me. Huh? Okay. All right. Good. All right. So we're going to spend time on a lot of different areas this time, and this is so much fun for me. All of these areas are so much fun for me, and I collaborate with a number of you guys. But this is what I do. I mean, essentially, this is what I do. This is my camera. It includes targets and sources. It includes the atmosphere. It includes optics, detectors, electronics. It includes displays. It includes human vision. I am not an expert in any one of these things, but I work with the experts in every one of those categories. And it comes down to how do you optimize the performance of such. And the first thing I ask students is, what are you limited by? Are you limited by the detector? Are you limited by diffraction? Or are you turbulence? Crane called me one time and said, Ron, we got a mid-wave camera, a long-wave camera given the same range performance. I'm like, well, they sent me their decks, their calculations. They were turbulence limited. Turbulence will limit your performance of mid-wave versus long-wave or any other band. So the importance here is all of these have to be considered. They have to be optimized. I'm going to pick on Dave Brady a little bit because I'm a big Dave Brady fan, but they used to invite me to the computational imaging workshop once every 5 years. I couldn't come every year. I could come every 5 years, and it's because they'd say, hey, not Dave, but some of the computational people, they'd say, would you teach us about how you calculate the performance of these systems? And I would come, and they said, please don't come back for another 4 years, 5 years, because they were working multi-aperture, multi-camera performance. There's 152 parameters that go into the calculation here for a single aperture. So it's hard, you know, and then now you're going to multiply this by 30 to 60 to 100 apertures, which they've built cameras that do that kind of, and it's extremely hard. How do you optimize that? So anyway, what are we going to talk about? I split this into 3 different areas. We're going to talk about military imaging in general, which is the infrared and military imaging are the same in most cases. And then we're going to talk about some advanced infrared systems, and then we're going to talk about some work that's being done here at University of Arizona. All right, so what is target acquisition, which is kind of my specialty? Target acquisition is I'm on a platform. This can be a soldier, it can be a tank, it can be an aircraft, it can be a ship. And I go into an area and I have to find the target. So I'm in wide field of view and I have to do search. Once I find the target, I've got to go to narrow field of view, and this is a complicated process. I have to go to narrow field of view and I have to positively identify the target before I shoot it. That process is target acquisition. Okay? What are the metrics associated with target acquisition? You can see here that I've got probability of recognition, probability of identification as a function of range. That's what the warfighter wants to know. What does the engineer want to know? What's your detectivity? What's your spectral response? What's your pixel pitch? What's your aperture diameter? Are you diffraction limited? Are you aberration limited? All the things associated with sensor performance, you want to know what that is. But what is the goal? And the classic goal is, can I tell a T-62 tank from a T-72 tank? Can I discriminate a tank before I and you absolutely have to. And there's a lot of academics that think that this process, maybe an example here is, you know, in, what was it, the first Gulf campaign or the second Gulf campaign, a U.S. aircraft shot a British APC, and it killed 4 people in the British APC, armored personnel carrier. You positively have to identify a target before you shoot it, okay? And that's what this is, and it's a model for doing that. It includes all of the components that I talked to you about. What are the bands? We've got long wave, we've got mid wave. Those are 2 classical bands. How do you choose? One of the things that I spent most of my career doing is, how do you choose long wave versus mid wave for a target acquisition platform? And most of you know that the Navy's mostly mid wave, Air Force mostly mid wave, and the Army's mostly long wave. Why is that? And it is because most of these systems are diffraction limited. If you're out of the atmosphere and you're at a high altitude and you've got clear air, then you really want some, you know, it's D and lambda. It's aperture and lambda for your angular resolution, right? But if you're down in the middle of all this stuff, you're in the soup. You've got smoke, you've got hot targets, you've got turbulence, you've got all these things at longer wavelength, and actually ends up helping you get through some of that. So there's a lot you have to consider here. I will say my group's starting to study the reflected bands, visible near IR, SWER, and E-SWER, and I'll talk about that some. Is this a big area? Is target acquisition a big area? Lantern's on there. That's the one in the center. That's the one in the center top up here. This is Lantern. I went to work on Lantern in 1984, and Lantern at the time was a $4 billion program, just for the targeting pod and the navigation pod. It allows the pilot to fly at nighttime, allows the pilot to do targeting at nighttime. And now you multiply that times Joint Strike Fighter, F-22, shipboard systems, Predator, dismount systems, tank sights. How much money are we talking about? It's a fortune. It is huge. Target acquisition is not some small area. And I will say, for some of you that are interested in studying this kind of thing, you can get a job anywhere tomorrow if you understand infrared systems and target acquisition. Okay. All right. How do I calculate the range performance of a target acquisition system? You've got a target. Target's got a characteristic dimension. It's got a contrast. It can be reflectivity or emissivity. You've got some range. They're associated with this target. This is not really a target. It's a target set, which means a collection of tanks or a collection of people or a collection of handheld things. When they're IEDs, it was a collection of roadside objects. Anyway, there's a thing called V50 or N50 that describes how hard it is to discriminate those things against each other. You propagate that through the atmosphere. What does the atmosphere do to you? And this is one, when I teach infrared systems, it cuts your light. It may add some light that's noise or background. So it reduces your light. It adds some light. It blurs. Turbulence blurs you out. Scattering can blur you too. Okay, so maybe you've got an MTF associated with that. And then this, the system contrast threshold function of the sensor, is described by everything that is in that camera. Aberrations, diffraction, detector blur, display blur, human blur. If you design a very expensive infrared system that is eye limited, you should be fired, right? So you can, in most of these high performance extreme dollar systems are diffraction limited systems, which means you got to have good optics design and you've got to have good integration and that sort of thing. So, all right. So once you compare your target contrast to this, and you've got a target angle, which is this characteristic dimension divided by range, you end up with this. This is what contrast you can see with the sensor. And like I said before, there's 152 inputs that go into this calculation of system contrast threshold function. It's what my target provides divided by what I can see with the threshold. I take the square root of that and I integrate it across spatial frequency. Okay? And this is a technique that Rich Fulmerhausen and we put this together. If you design a military system today that is a targeting system, regardless of whether it's reflected or emissive infrared, you have to use this in your design. And it's called the TTP, Target Task Performance Metric. Before then, it was the Johnson criteria, and the Johnson criteria was cycles on target. I need 6 cycles on a tank to be able to see it and identify it at a 50% probability. It was just this point at which the target contrast and your sensor contrast cross, and it was not good enough. And I'll tell you, from a historical point of view, they were fielding platinum silicide sensors versus NSPE sensors, and this bathtub changed shape, and there was a lot more information. Where when you hit the Nyquist rate, this can be limited by the Nyquist rate here, and it gave you the same answer and range performance. So they had to do something to fix that problem, and this approach did fix that problem. So anyway, this calculation, the units on this is cycles per milliradian times milliradians gives you cycles on target. You've got a V, which is cycles on target, compared to V50. That transfer function provides you with a probability that is a function of range, and you do this over and over again as a function of range, and that's how you calculate target acquisition performance.
That's the number of cycles necessary for that 50% probability.
That's right. Yeah. All right, so what goes into the CTF of that, the contrast threshold function of, this is your eye. You can kind of see where the contrast, where you can see the spatial frequencies and where there's a limit where you can't. Now if I add blur, which is my optics diffraction blur, my aberrations, my detector, all of that blur has to be and that reduces the spatial frequencies that you can see. And then when you add noise, all detectors have, you know, you got blip noise, Johnson noise, you got readout noise. There are a number of noise components, and when you add those in there, you end up with, this is the CTF of your system. Now I will say, some systems, the noise, signal to noise is so good, you're not going to see the noise. In that case, you're back, there's two equations in the CTF. One is an eye-limited equation, the other one's a noise-limited equation. And this shows you what the equation is. This is the eye limit, this is the noise. There's two of these CTF curves. The two CTF curves, you take the geometric mean. The higher one wins, and it's the limit of, you know, so you can have a system that's kind of a eye contrast threshold function limit, or you can have a noisy sensor, and that's a noise limit. All right, we're going to talk about a number of different things, and I'm going to try to transition these. I'm trying to give you a decent background in infrared systems. ISR in the military is called intelligence, surveillance, reconnaissance. Some people call it remote sensing. I'll talk about where these used to be, but now where they're at is, to me, it's very, very interesting. And since 1995, things have been changing dramatically. John Lichtenauer was the chief scientist of NEMA, National Imagery Mapping Agency. That is now called National Ground Intelligence Agency. As you guys know, the Defense Department satellites, most of them are designed by National Reconnaissance Office and built and then deployed, and then NGIA operates them. The way it works is our COCOM commanders around the world, they'll say, NGIA, I need this, this, and this, and it's a task list, and whenever these birds fly over, you get imagery. Okay, well, the imagery, what is the purpose of a classic ISR sensor? It's to eat up as much ground as possible in as little time as possible with enough resolution to do the job that you're trying to do. Okay? How do you communicate to NGIA what job you're trying to do? It's a thing called NIRS, National Imagery Interpretability Rating Scale. I need an image at this location, this time tomorrow, with a NIRS level of this. Okay, and you can see these are unclassified NIRS level. This is in the book. I'll show. Well, it's a book that John Lichtenauer and I wrote, but it's there are a classified set of these NIRS levels, and it's in a book that you can task these sensors to do. There's an infrared version of NIRS. There's a EO version of NIRS. There's even a radar version of NIRS, and it's I think that's all I want. But I do want to tell you, in the year 1995, when I showed up in D.C., and I spent 20 years up there, and I worked both the ISR community, and I worked mostly target acquisition, but I did ISR some. There was an altitude, 12,000 feet, right around here, that you had a community that owned the sensors above there. You had a community that owned the sensors below there, and this was target acquisition. You see the PR, that's probability of recognition, and you see the NIRS. The sensors above 12,000 feet were designed with the general image quality equation that John Lichtenauer developed. I showed you the process that Johnson's criterion that Volmerhausen and I developed for the target acquisition community. But you had to be able to talk, what does a NIRS 5 equate to in the probability of recognition of a tank? So I did a lot of those conversions for a bunch of the agencies up there. But then came along Predator. Okay, and Predator, I wish this graphic were a little bit better, but Predator was the first platform to really specify the sensors on board in terms of NIRS and target acquisition. They had a specification for both. And it wasn't long. Predator was developed as an ISR platform, and it was used for that for a good 5 years. And then they put Hellfire on it. Okay, so they weaponized Predator, and that's one of the very common weapons that we use today. We use that more than we do other very high, expensive weapon systems. Okay, so now this line, this 12,000 feet is blurred, and we do targeting we're doing targeting from high altitude now. And, you know, with the hypersonics, this, you know, Dr. Phillips is working, you know, imaging hypersonics through turbulence and a lot. This line is blurring and it will never be the same. So, all right, then came along persistent surveillance. What was that? Well, we had these IEDs on the roadside bombs. We had personnel, people-borne bombs, you know, suicide vests that go in, and we had vehicle bombs. We had a number of events that were very effective. I call it a military technology war against commercial technology, and commercial technology is pretty good. Okay, so what persistent surveillance, and I had two programs at the time that I was in charge of. One was Angel FLIR. Well, ARL had Constant Hawk, and they transitioned that. Mine was Angel FLIR, which was a Marine Corps program at Naval Research Lab. But the idea was something like this. And they were infrared because they wanted to see at nighttime. You fly circles over a city, and you sit there and take an image once a second or once every 2 seconds. The rate has to support, can you track a vehicle and can you track a person? Okay, so what you do is you sit there for 24 hours, and I mean, some cases they would do it 12 hours or 8 hours, and the pilot flies circles. It had to be the most boring job for a pilot ever, right? So they fly circles, an event happens, they rewind this thing, and then they go back in the morning. The Marines go back in the morning and they raid where they need to. It was very effective. It was a great program. They still exist. I think it changed into, currently it's called Gorgon Stare, and it is a classified program now. You won't hear much about it anymore. But it was, for what we were doing, it was very effective. Okay, infrared search and track. This is one that I'm working now. I'm working two programs with this, but it really is the detection of aircraft, and it's a detection in the offensive mode. Most of our adversaries have really developed some radar and electronic warfare capabilities to the point where now you need to go passive. You need to just not use radar, electronic warfare, but you need to detect these things in a passive way. Okay, well, what does that mean? You're looking at the infrared signature of these aircraft passively, and you're soaking the photons up, and you want to detect it and know what's there and track it, okay? And you can do that. You can do that up, I don't know, 100 kilometers, 100 miles. It's very effectively. And the optimization of currently the only fielded infrared search and track systems are scan systems. They scan back and forth, and now they're being replaced with staring systems. There are many reasons why you cannot design a staring system that will just look 90 degrees and stare and give you the performance of a scan system, and it's all about aperture. Aperture is the most important aspect of that, and it's a squared function compared to a direct function with detectors. And big detectors, you'll hear some people say big detectors are great at infrared search. The reason big detectors are great, big detectors come with big apertures. That's the only reason big detectors are great. So anyway, this is a very interesting area, and the key is, what is your optical blur spot compared to your detector size? How do you optimize that? How do you do tracking when you're in a staring array and you're at the edge of a detector? You got, you can have match filters, on and on and on. So, pilotage, okay? Pilotage is flying, for infrared people, pilotage is flying at nighttime. You can calculate the performance of pilotage, and this is using the TTP metric that I described to you earlier, but instead of using a target contrast, you use your background contrast. And I know my graduate students have been outside and they're measuring contrast of buildings and trees and that sort of thing, but your background contrast, the more contrast you have, the better pilotage you can perform. And you think about Apache. I'm working with Apache currently, and it's a head track system. This is your targeting system. This is called PNVIS, Pilot Night Vision System. When the pilot turns his or her head, this thing moves. The thing follows your head around as a head track system. And this is a typical calculation for pilotage where this is high contrast, this is low contrast. What does high contrast look like? Well, it looks like this scene here where you've got, today outside in Tucson, there's high contrast out there. Your buildings are hot, your grass is cool, there's a good 10 or 20 Kelvin of contrast out there. But if it's been raining and it's been the same temperature for a long time, your contrast can go down to where it's like less than a Kelvin. And you have to fly that aircraft with less than a Kelvin of contrast. You've got to have good capability. And there is a threshold on this TTP at which a pilot will not take off. So what we're doing now is, instead of this gimbal and this thing following this head track around, now we're going to put 3 cameras in the front of the aircraft, and you're only going to see the information that you need to see with the helmet. So, and you think that, hey, that's a simple thing. It's not a simple thing. Integration time, blur issues, what's the vibration of that platform? There are many things you have to calculate, experiment, and then go through. And Professor Brady and I are working on how do you make such a large pixel count with good resolution. A lot of his work with the super cameras and all, if we take that to the infrared, there's some good opportunity there. So I'm only going to say a few words about threat warning. Most of our high-value platforms, aircraft, have threat warning on them. Okay, and in aircraft, it's called infrared countermeasures. Okay, so what is that? Someone shoots an anti-aircraft missile at me. I got to do something about it. Okay, most of them are infrared seekers. So what do? You can do 2 things. You can pop flares. Hopefully this thing follows one of my flares. These things are getting so smart now that the flares aren't working so well anymore. Or you can point a laser at the seeker and you can jam it. You can give it a signal that it thinks it needs to turn left, and it turns left, right? So you can do those 2 things. But from a sensor point of view, an infrared sensor point of view, how do you detect these things are coming at you? Okay? And it is all mid-wave because these propellants and that sort of thing have nice spikes in. You all know Planck's curve. Planck's curve shifts to the left as things get hotter, and things seem to love mid-wave when your propulsion or explosion or hot things end up loving mid-wave, and that's where they are. And there's spikes in there that you have to detect, and you can do something about it. But a lot of you in here know that mid-wave comes with a cryocooler. Long wave has gotten where you don't need a cryocooler with the uncooled microbolometers. The performance is good. But for mid-wave, if I've got a cryocooler and I've got 6 of these things around an aircraft, you got $1 million system, okay? And it turns out that Israelis in Tel Aviv, they're actually putting IRCM systems on some of their aircraft because they feel it's worth $1 million to put on a commercial aircraft an anti-missile countermeasure, okay? They're the only people I know that are doing that. Okay, but what about ground combat vehicles? None of our vehicles have countermeasures on them. Matter of fact, we don't have a sensor on there that can tell whether you fired an anti-tank missile at me or an RPG. We've got armor on there, but that doesn't seem to work so much anymore. So the Israelis have done a great job with ground combat vehicle countermeasures. What they do is this trophy system has these little, I mean, you guys know the radar on cars now. They're so cheap, and they can tell when the car is in front of you. They got a number of these things pointed around the tank, and they detect when something's coming into the tank with the radar on. And then they got a little thing that's kind of like a shotgun shell, goes over, and it destroys the shape charge. It damages the shape charge, so it's no longer effective, right? The United States will not put radar on their tank and leave it on the whole time. They will not do it. It gives away the position of your tank. So what they need to do is provide a wake-up sensor in the infrared. Lead selenide was definitely a possibility, but there's too much 1/F noise in lead selenide. I think probably what's going to happen is type 2 superlattice in the midwave. The operating temperature now is somewhere around 160 Kelvin, and people keep getting that up to the point where now maybe you won't need a cryocooler very soon. So, Okay, we've talked about military imaging and infrared systems and military. What are some of the new things? Third Gen FLIR. Third Gen FLIR is not deployed yet. It's pretty close to being deployed if the program doesn't get killed. The first generation FLIR was a line of detectors that was scanned back and forth. There were 3 versions of it. It was called Common Module. There were 60 detectors for ground combat vehicles, 180 detectors for aircraft. In some special cases, there are 120. So there were 3 different versions of first gen FLIR that were common module detectors. Second gen is 480 lines. The lines are interlaced to where you've got the staggering. You're oversampled. So you got 480 lines against 1,300 samples across the horizontal field of view, and that's what's fielded today. It's a great system. It's in Apache. It's in M1 Tank. It's in Bradley. It's in all these things. Third gen FLIR, which is done with research and development, it's finished now. It is not in production. It's getting ready to go in low rate LRIP, low rate production. But it is mid-wave and long-wave on the same chip. Each detector has 2 colors, and it's got a digital readout integrated circuit, so you're getting digital information instead of an analog. It has a lot of field of views, and it worries me because last I heard there's like 14 optical elements, and you've got these 2 very different chromatic wavelengths going through this thing, and the production is just unbelievable, and the cost of that optic is just, it may end up sinking the whole program. Okay. Not only that, you got mid-wave and long-wave in the same camera. You can't have the same F number. Okay. Your cone of, you want with mid-wave, you want an F number that provides you long-range identification because that's your diffraction limit. And then you want to use the long-wave to do all this dirty battlefield stuff. Okay. And I was chair of the third gen FLIR IPT that determined the performance at third gen, and I'll tell you just a real quick story. When I was at Night Vision Lab and I became division director, I was like, what the hell is this third gen FLIR? You guys tell me what it is. And Fred Petito, who's airborne division, goes, oh, Ron, that's easy. You do search in the long wave. You know, you look around and very quickly, you know, there's so many photons in the long wave. You do search, you detect the thing. Then you go to narrow field of view and you do the long range ID. Okay, everybody knows that. I'm like, I didn't know that. So I went and did these calculations, and it turned out mid-wave by itself did pretty close to what third gen FLIR did. So I went back to we had a division head, the whole lab, all the division heads had Monday morning meeting. And I went back, and Fenner Milton was our lab director. I said, Fenner, do you mind if I show all these guys some calculations? And he said, yeah, sure. So I showed this mid-wave did real well. Night Vision Lab's always been a long-wave house. They didn't like it one damn bit. And some of the division directors said, Ron's new. He's a new division director. He doesn't know what the hell he's doing. You're not going to let him present this outside the lab, are you? And he goes, not only is he going to present it outside the lab, he's now in charge of third gen FLIR. He's going to tell me what good it's for. So this list here is kind of the reason I told you that story. Is immediately all of these old timers that had been studying thermal imaging all their lives came to me and they said, this is good for that, and this is good for that, and this is, I'm like, okay, where's your report? Where's your data? Where's your paper? Where's your presentation? Oh, we did this in the back parking lot. Like, no. You didn't write it down. You didn't do it. If you don't take a picture, you weren't there. So, and I feel that same way with my grad. Every one of these issues has a paper now, and it determines the performance of long wave versus mid wave in turbulence. You're photon starved in cold weather. If you're fighting in Alaska, are you going to use long wave or mid wave? What happens when you've got smoke? What happens when you can see the list, you know? So it's all of these things are pretty much ironed out. Third gen's a pretty good thing. So Stu Horn and Nabir Dar at DARPA. Your phone's ringing. So. Hey, Brian. anyway, Nabir Dar and Stu Horn at DARPA, they used to come to me all the time, and they would say, hey, Ron, I want to know how small a detector we can make and it still be good in the long wave or mid wave. And I started doing these calculations and all. And I realized that if you can, yield for a focal plane goes with chip size, centimeter squared. Okay, that's the number one thing. And part of it's dust on a readout integrated circuit. Part of it's integration and that sort of thing. But after I started looking at this, if you can make a chip size that's the same size as the chips that are currently available, and you can make a detector pitch that is extremely small, you can design an infrared camera that has a wide enough field of view to do your wide field function, and then zoom in electronically into the pixel and get diffraction limited resolution for a narrow field of view without switching optics. And here's the thing I want to tell you. I told you about target acquisition. I'm doing search. Okay, I'm doing search and finding my target. Once I find my target, I've got to center that target in the center of my field of view, which takes about half a second. And then when I switch fields of view for a military armored system, that takes about a little over half a second. I've got to do the identification. I've got to go back to wide field of view and then continue my search. And if there's 20 things out there that's clutter and targets, I've got a long process. Okay? So if I've got small pixel with a large format focal plane, all I've got to do is touch screen on this and they just pop up. I do my interrogation and I move. And matter of fact, I can have an ATR running on the whole display the whole time. A typical field of view of an aircraft and the medium field of view is 7 degrees, 7 to 8 degrees. Narrow field of view nowadays is down to half a degree. A ground combat system medium field of view is about 14 degrees, 14, 15 degrees. And then the narrow field of view is a factor of 4. So what I'm telling you is this saves you so much time. This is first gen FLIR performance in terms of identification range. This is wide field of view. This is second gen. This is third gen. The reason third gen went so much further than second gen is we went to midwave. Remember, I told you third gen had midwave in it now, right? Okay, but what happens if I can do long wave with an F lambda over D, and I'm teaching my students that diffraction limited imagers have an F lambda over D of 2, and I'll show you why, but this is what you can get. You can get a wide field of view with a long range identification. This is a sensor that was developed by DARPA. DRS did the development. It's a 5 micron pitch. I had people say, hey Ron, what the hell are you doing? 5 micron pitch, 10 micron wavelength. That thing's not going to work. Come on. You got a diffraction spot on this table and you tell me where the photons are hitting this table, I can tell you where the electrons are going to be generated. Okay? So now reticulation may be something different, but you have to consider these things. All right, so if I set my optical cutoff at my 1 over my detector IFOV, this is what happens. This is my half sample rate, my Nyquist rate. This is all aliasing, okay? And I can look at your image and I can tell you whether you're most of you should be able to, most of my graduate students, I definitely want them to learn. I want you to be able to look at an image and tell whether there's aliasing in there, okay? If I set my optical cutoff at my sample rate, my Nyquist rate of my detector, and I set this is F lambda over D is equal to 1. So I've got aliasing at F lambda over D is equal to 1. If I set my optical cutoff, D over lambda, equal to 2 times my pixel pitch over my focal length, then this is what I consider a diffraction limited system. Okay? And if you rearrange this is an F lambda over D. F is F number, lambda is wavelength, D is pixel pitch, that's equal to 2. Okay? That's the way I will define diffraction limited. And I will tell you the reason why I define diffraction limited that. I get these people all the time coming and saying, Ron, listen, your blur spot's 4 detectors. I ought to be able to identify that thing. Okay, well tell me how. Tell me, what is your calculate? I know Sparrow's criteria. I know Rayleigh's criteria. I know you can separate stars using these spatial criteria. But there has never been an extended source target acquisition model, discrimination model, that was not frequency based. They're all frequency based. Okay? And in the old days, this was true. how do you make a sensor see further? You make a longer focal length. What happens to your F number? It goes up. So higher F number is longer range. Lower F number is wide field of view, shorter range. It's not true. I'm here to tell you it's not true. Okay? Range goes with F lambda over D. In this angle, the inverse tangent of F lambda over D, it goes up linearly with it. Your range performance, how far you can identify a target if you've got enough light. This is long wave. This is your F number. This is your F lambda over D is equal to 2 line. As you come around this angle, theta, this is calculated range performance with theta. And notice 3-inch aperture and 6-inch aperture look the same. If I had a 12-inch aperture, it'd be double that. It's that simple, okay? And it took a long time to figure this out. Cell phone people have known this forever, but you know, they've had very, very small pixel pitch, and they're not diffraction limited, okay? In the infrared, we're pretty much diffraction limited. So what can I do now? Okay, I've got good chips. Apache is building a 6K by 4K, 8-micron pitch focal plane for targeting now. That's going to be their next targeting sensor. And I'm very happy about it. You're going to see that this is going to be 4th Gen FLIR. I'm sure of it. Okay, so what can you do now? I've got a field of view there, medium field of view, wide field of view. I'm doing a search. I do touch screen. I get the target chips up. I do my identification. I let an ATR run on the background. I don't have to trust the ATR. I can human discriminate all these target chips and move on. So that's small pitch, high density thermal imaging. The other thing that's come along is digital ROICs. What good is that? Well, all of these focal planes have capacitors on them, and the capacitor has a limit of how much charge you can have. And a lot of people don't know this. In the long wave, if you've got a photon detector imager, you only use 1 photon out of every 10. I throw away the rest. We've got way too many photons in the long wave. Now, can I gain those photons if I've got a longer integration time or a deeper capacitor? Yes, you can, or a digital ROIC. Okay, and that goes from this to this, or you can have a higher frame rate and integrate for the capacitor size. This is harder to do because you're talking about huge data rate coming out of a cryocooler. Okay.
What's ROIC?
Readout integrated circuit. It's the silicon chip behind your infrared detector focal plane. So, okay. So, sorry, I know I'm probably using too many acronyms here, but it's a lot of information. So Don Riego at Night Vision, he's the director there now. He wants to use all of these photons to be able to see through things. Dust, smoke, rain. But Raytheon called me and they said, hey Ron, listen, we don't want to see through all the stuff, but I mean, it's okay if we do, but what can you do with the deeper wells, the more electrons? And my thought was, I showed you the CTF earlier. Can we correct this MTF using that additional signal to noise ratio? Can we correct this MTF to where you end up with a better contrast threshold function? And we did that, and I've got a graduate student who did that, and he finished his PhD last year. And we proved, yeah, you definitely can get a huge benefit from that, but nowhere near as much as the TTP would calculate. And the thing is, the model that I showed you earlier, it was not developed for severe boost. So that's what the issue. But you're providing a huge gain at the high frequencies of the image. So okay. But I don't know if you can see this that well, but you can kind of see what it provides to you. Yeah. F lambda over D.
You have these static images and your pixels are small. I can see that it's hard to beat the diffraction limit. But if the target is moving, or if you're deterring the detector, don't you have an advantage there because you have small pixels and then you can look at the differential signal?
You can. I mean, you've got to have a very short integration time. You know, I mean, there's a lot of factors that you have to consider, including integration time. So, but yeah, I think so. Yeah. F lambda over D. I am a big proponent. This FET, F-I-E-T, first wrote of F lambda over D, and he got the King's Lake Award for optical engineering, something like 15 years ago. And then Jerry Holst went and he made this 6-order polynomial. And essentially what this is, F number, wavelength, and pixel pitch, it is a measure of how close to being diffraction limited you are. Okay, once it hits 2, then all of my students know that your range performance is really, there's only 2 more knobs you can turn. One is your aperture diameter and the other one's wavelength. Okay, but if your F lambda over D is less than 2, then you're pretty much IFOV. IFOV is instantaneous field of view. It's your detector angle seeing out in space. You're IFOV limited. Okay, so I like it because you can sit there very quickly and tell how do you optimize a sensor that's already been, what can you do to enhance a sensor. Okay, so that's the advanced systems. Let's talk about some stuff we're doing here at the university. I wrote a paper not long ago called What Good is SWER, because I had an admiral come in my office and say, Ron, I need those SWER sensors because BAMS, which is the Global Hawk for Navy, can't see through clouds. I want to be able to see through clouds, so please get us those SWER sensors. I'm like, you can't see through clouds. And so I love the paper because I got to work with Janet Shields at Scripps, who's the cloud expert in the nation. I got to work with NIST, who are the smoke experts in the nation. They burn couches, they burn wood, they burn everything, and they measure smoke, and it's just awesome, you know. So, so we went through a lot of that, and the thing is with the reflected bands, when the sun's behind you, there's 2 things with the reflected bands that are not going on with the emissive bands, the midwave and long wave. You got atmospheric transmission, which is reducing your light from your target, and in addition, the sun is dumping scattering that is filling up everything in your camera, and it's horrible. You're taking a double hit on your reflected bands, and especially if the sun's behind you and it's doing forward scattering, it's just awful. Well, if you calculate the SWER is affected less by that because it's longer wavelength, and if you calculate tank ID as a function of range, SWER actually beats visible and near IR, and that goes against what everything that you guys have learned and everything I've learned. Because if you're a diffraction limited system, it's less resolution. Well, I showed you the TTP metric, and your range performance goes up. Resolution definitely helps you, but dynamic range also helps you. And if your dynamic range goes up 100 times and your resolution decreases by 2, you can identify a target further. Okay? This is full spectrum targeting, which is the future vertical lift targeting system. Okay? Here's, I worked at Night Vision Lab used to spend a week up there a month doing calculations for them. And you see SWER, these numbers are the range in kilometers at which you can identify the target that they're looking for. Okay, and this is under dust, smoke, rain, fog, all these conditions. This goes along with Don Riego's dream of, we used to own the night, we don't own the night anymore. Now we're going to own the weather, right? So SWER does great. And in doing that, Lindsay and Patrick and I have been looking at these different reflective bands. If you're in the reflective band, so like a Raytheon ball or a L3 Harris ball, the large balls that go under long-range aircraft, long-range imaging aircraft, the way that the reflected bands are designed is you take the most narrow infrared midwave band and you half the field of view for your reflected bands. And that allows you to see much further than the infrared, which kind of makes sense, but you are not diffraction limited. That's the point here. You're not diffraction limited. You are scattering limited, scattering and absorption limited, and that's this line here. All of these degraded conditions as a function of wavelength, you get better performance at longer wavelength. Until you hit diffraction, then your range performance goes down. And I love this chart. Patrick Leslie put eSWER on here. eSWER is something I'm very interested in studying. And what this is transmission, atmospheric transmission. This is whatever band near IR SWER, eSWER. This is the atmospheric transmission in the visible, and there's 2 ways to come down this curve. One way is longer range, And the other way is if you've got a harder environment, 5-kilometer visibility, like you're flying through Los Angeles, you've got a 5-kilometer visibility, so you're coming down these. You see the eSWER sometimes has, 1,000, 10,000 times better transmission than you do in the visible for these long range. This is the reason the U2 and Global Hawk both have SWER sensors on there. If you're looking long slant range, that's it. So Dave showed the long wave and mid wave, and I think some of these, but you can see visible, the visible band, you've got so much haze there and so many things that you're having a hard time seeing the mountain, okay? In the near IR, it's better. In the SWER, it's even better. And we're starting to get some imagery. Lindsay's starting to do experiments with eSWER. We are putting together 2 test beds. One is a 20-degree test bed, and one is a half-a-degree test bed for doing extremely long-range target identification. You've seen the grad students out front of the building, and you can SWER grass looks white. Reflectivity is very high. I think you should do tank search in the SWER. I told the Army that. They're not interested in it. But this is eSWER, which is 2.1 to... Extended SWER. Yeah, I should have mentioned. 2.1 to 2.4. I chose that because there is a beautiful window in 2.1 to 2.4, and the atmospheric transmission is very nice for that. But compared to visible, you only have about 8% of the light from the sun, and that. So it's not just atmospheric transmission. What is your reflectivity? What is your sensor performance? How much light do you have? You have to consider all those things. So. And then this is Charles. You can kind of see there's some nice differences there. I want to talk about drones a little bit. We're hanging all different kinds of bands on drones, and we've got a program with Army Research Lab, and there's 2 operations here. One is you send 4 or 5 drones in to cover a battlefield, and how quickly can they do it? And it's large area coverage. It's not narrow field. This is all wide field stuff. And then once you detect some targets, then you send a second set of drones in there with magnetic sensors, acoustic sensors, imaging sensors with polarization sensors, all the sensors to interrogate these targets and really because a lot of people don't know in Sarajevo, when the United States got involved with Sarajevo, 70 to 80% of the ordnance that we dropped on those targets, they were blow-up targets. They were decoys. And ordnance is very expensive. A Tomahawk missile is over $1 million. So anyway, we're building a capability here to test out some of these concepts here at the university. And we've got some infrared quadcopters. I'm excited about the fixed wing. Professor Brady and I and the graduates, his graduate students, we designed a 4-camera wide area without a gimbal. Can you do this without a gimbal, lightweight? How do you optimize large area coverage and interrogation? And this is some of the imagery. We've got a tractor over at Relito Park that we use for a target. That's our tank. Will this play? I was hoping these would play. We're working with some retired colonels, A-10 colonels over there, and they're having a blast flying these cameras for us, But we do have an Albatross. This is Ucfs Albatross. We matched Memphis's and Ucfs Albatross. They're not. This is a $15,000 drone, Apache is now launching drones from Apache, and we thought the rotor wash would just slam the thing, but it does well, and it goes out 20, 30 kilometers and tells Apache, hey, is there a air defense unit up there? So wide area coverage sensor design is a big... What's that?
Do they try to catch them again, or do they send them off?
There's two versions. One is a high dollar version. One is a cheap disposable version. So pilotage. One thing I want to show you guys. I told you about strap down, and I think a dual band ahead of the aircraft, and then cheap uncooled microbolometers on the side. But this is data that our drone, our infrared drone, took. Let me see if I can play this. Notice that you got hot wires up there. Wires are a major issue. Is it going up? Watch these wires disappear into the path radiance of the atmosphere. They're gone. They're gone. And can you imagine a helicopter pilot flying right into those things? Now I'm going up, and I'm going to look down at the wires against the hot ground, and it's going to reflect cold sky. And Patrick Leslie and I have a modeling paper of how you calculate the radiance coming off these wires and what the visibility is. And, you know, dual band really makes sense because your path radiance in the atmosphere is different. One of the PhD students I have is studying python detection, snake detection, and it's because there's 300,000 of them in the Everglades. We chose 850 nanometers just for the camera because your foliage has high reflectivity and your snake has low reflectivity. You can kind of see how the thing works there. This is an inverted image if you were wondering. And then let me see if this will play. This is a drone with a near IR 850 camera, and you definitely can see the pythons. This one is not inverted, so I don't know if you can. Can I see the? I see two things. It might be a snake there. But the high reflectivity of the foliage really helps you. It robs the snake of its camouflage. That's what it does.
But pythons are infrared detectors themselves, right?
I wouldn't know. It's a good question. Maybe. Yeah, I'm not sure. So. Okay, there's a lot of things I did not talk about. I mean, this is kind of the end of the thing. I do want to say that my graduate students are wonderful. They're the reason for most of my success lately, and they're just such a wonderful group. I've got some of them from UCF are still with me, and then the ones that we've got here at Arizona, I would call them the dream team just because they're very capable. And then the collaborators, you know, Dave Brady, Ron Phillips, we've got some really good collaborators, some at Memphis and some down at UCF. So, but let me just say goodbye, everybody. I've got to go. They sing pretty good too. You know? Gotta leave you all behind and face the truth. I think some of us can go into different areas. I don't wanna die. Anyway, that's it. Any questions? Patrick, I cut that down to something that was a lot shorter.
And not a question. It is a welcome to you. I can't speak for Dirniak when you mentioned it earlier, but I can speak for Bill Wolf, and I welcome you.
Bill, I'm thankful to be here, and it's an honor.
And I'm looking forward to good stuff.
I guess I can speak for Dirniak. I'll second that.
All right, we got our two giants here. This is awesome. Thank y'all for staying. Thank you and Bill for coming. Really appreciate it. All right, any other questions?
Is that a deep fake up there on the? I don't think that's
Is that a what?
deep fake.
Deep fake?
Yeah, one of those fake videos, or not the real people.
Are you, Kevin? Are you saying that's not you?
I don't know.
Sensors, what are the materials that you use for this short range and long range?
So that is a really good question, and that's changing very rapidly because, and I know that academic people define midwave that includes everything, you know, sometimes everything, but in the military it's really defined by the materials. Silicon cuts off at 1.1, N-gas cuts off at 1.7, To get out the E-SWER, our E-SWER is mercad telluride, which is an alloy that you can tailor for any wavelength that you want. Midwave is going through a revolution right now. I don't expect NSB to be around for much longer. Type 2 superlattice is really coming along, and the operating temperature for Type 2 superlattice is about 150 Kelvin or so. And then in long wave, there's a revolution in microbolometer technology. The performance of a microbolometer is described by the tau NETD product, which is the time constant times the noise equivalent temperature difference. And those are down now to 200 or 200 millisecond millikel. It's just
How are
phenomenal.
they improving?
They're getting down to something that is very, not single layer, but pretty close to a couple molecular layer. They've got a process that makes it,
The absorbing material?
yeah, the absorbing material, yeah. All right, any other questions?
The arrays are more like CCD or photodiode arrays. What is the physical mechanism on which they operate?
I mean, microbolometers are a thermal detector, whereas the rest of them are photon detectors, you know, and then the Type 2 is a quantum engineered structure, you know, so it really depends on what you're talking about. It depends on which one of those material solutions that you're talking about.
Like CCD
Yeah.
that you have in silicon?
Any other? Listen, thank you all very much for coming. I really enjoy, you can tell I enjoy this work very much, and I'm happy to share it with you guys. So. Thank you.